Dean and Staff, Faculty of Geological Engineering, and the honorable speakers and participants. Assalamualaikum warahmatullahi wabarakatuh, and good afternoon. Welcome to the International Webinar Series 1. This session is part of the webinar series in a context to the 62nd anniversary of Geological Engineering Universitas Pajajaran with the term melestarikan bumi dengan sumber daya manusia yang berkualitas. Today, we have these speakers from different countries, Japan, Philippines, and Thailand, that will talk about the topic mineral and energy resources for the future. Before we start the webinar, I would like to explain the rule during this event. First, the microphone has to muted when the speakers or moderator or MC talks. Second, the question can be written in the chat room or asked directly after the explanation from the speakers by reaction raise hand. Now, to begin this webinar, I would like to invite from Mega Fatima Rosana as Dean Faculty of Geological Engineering to open the webinar officially. Please, for Mega, stage is yours.
Thank you, Ibu Aton, for the welcome speech to the audience. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon to everybody. Greeting to all of us and to the honorable our leaders, members of our Senate Faculty of Geological Engineering, and also to our invited speaker, Professor Watanabe from Graduate School of International Resources Science of Akita University. Good afternoon, Professor Watanabe. And our colleagues, Dr. Engineering Jillian Gabro from National Institute of Geological and Science of the University of Philippines. Maybe she will attend in the afternoon for the second lecture, and also for Dr. Abis Salam from Department of Geology, Faculty of Science of Chulalongkorn University, Thailand, and he also will talk maybe in the afternoon. Our all vice dean, manager, head of laboratory, our head of the study center within the Geological Engineering Faculty, our lecture staff, administration, and our chairman of Alumni Association of Faculty of Geological Engineering, and to all participants within this webinar series, which I cannot mention all of you one by one. Praise and gratitude we pray to presence of the Allah Subhanahu wa Taala, who has given us His infinity grace and grief to all of us, so that we can gather together this afternoon to join the webinar series as a part of various activities in the context of our 62th anniversary of Geological Engineering Universitas Pajajaran, where the main event of the anniversary will be held in November 2021. This anniversary has the theme Preserving the Earth and Preparing Quality Human Resources as a form of the effort to increase the role and the contribution of Faculty of Geological Engineering, especially through natural resources, management based on environmental, and to support sustainable development and prepare human resources, in particular as superior, tough, and qualified geologists. This webinar series number 1 has a theme, the mineral as energy resources for the future. This theme is raised to remind all of us that the potential of mineral resources that are quite a lot, which also has great potential to be developed as an energy resources. As a part of energy diversification, besides we already have in oil and gas, coal, hydrogeology, and geothermal. In Indonesia has a fairly large For example, nickel laterite resources potential, which this potential can be used for nickel lithium battery, for example, which is used for various advanced technology devices nowadays, in development in everywhere. So in this occasion, I would like to thank to Professor Watanabe, my senior in the Association of Economic Geology, and our partner university in organizing the UNPAD Akita double degree program for Master in Engineering Geology, that he will enlighten to us about the mineral resources that can be utilized as energy resources that can be developed as energy resources for the present, of course, and the future to our life. I also do not forget to express my gratitude to beloved friend, Dr. Jillian Gabo, or I call her Jill, from the University of the Philippines, who has given, she will give an explanation about the potential of scandium and REE element, especially from nickel laterite deposit. With later, I think she will give the example study at the Infanta deposit of South Palawan, the Philippines. And lastly, I would like also to express my gratitude to my long-time friendship with Dr. Abisalam, or normally I call him Dr. Masu, for presenting his topic entitled Mineral Deposit of South Asia, which I think he will highlight it, the important mineral deposit belt in South Asia mainland, and the potential for exploration and mining area, and of course the energy potential as a part of the mineral. For example, maybe he will also highlight about the lithium potential. Hopefully, this webinar can provide enlightenment and benefit to all of us who attend this webinar, so that we can all start to identify and explore the potential of mineral resources, especially in Indonesia, which can be developed as environmentally friendly future energy source for Indonesia. Thank you very much. Billahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Mega, for the opening speech. Okay, the next event is sing our national anthem, Indonesia Raya. Please, ladies and gentlemen, stand. Okay, now let's proceed to the first speaker session. We're pleased to welcome Professor Yasushi Watanabe. He is from graduate school from Resources Science, Akita University, Japan. He will explain about mineral as energy resources for the future. This session will be guided by Dr. Santi Dwi Partiwi as the head of International Unit, Faculty of Geological Engineering. Please welcome Dr. Santi. The stage is yours.
Yeah, thank you very much, Ms. Aton. So, good afternoon, everyone. Assalamualaikum warahmatullahi wabarakatuh. Thank you and welcome to our college, friend and student here for taking time to attend today International Webinar Series 1 with the theme Mineral as Energy Resources for the Future. So, I'm Santi Dwi Pratiwi as moderator for today's webinar. So before the presentation began, allow us to introduce the first presenter, Professor Yasushi Watanabe. So Professor Yasushi Watanabe is specialized on economic geology. So on the 1982 was graduated from the Hokkaido University with the external career in the 2001 until 2003 has chief researcher at the National Institute of Advanced Industrial Science and Technology, Institute for Georesources and Environment. And now, for the campus career, Professor Watanabe is head of Department on Faculty of International Science, Akita University of Japan. So now this is the high time for us to listen presentation from the main speaker. So please welcome Professor Yasushi Watanabe. Time is yours.
Thank you very much. Very kind introduction. I'm very glad to have this opportunity, and I would like to explain the very drastically changing world now. Can I share the screen?
Yes, sir.
Okay. So the topic today is minerals as energy resources for the future, and I'd like to explain the background using a little longer time and why we have to develop several kinds of mineral deposit for energy resources. I don't need to repeat my introduction, but I was born in Kyoto of Japan, and I joined the Geological Survey of Japan from 1985, and I was working there as a geologist for nearly 30 years. And now I moved to Akita University and teaching geology, mineralogy, and economic geology in the school. This figure shows the energy production balance in the whole world. So we can see the total production of energy is increasing year by year. Probably this is according to the increase of the human population in the world. And if we look at the source of energy, we can see coal, oil, natural gas, nuclear, hydroelectricity or biofuel and waste, and others. But among these, majority of energy has been produced from coal, oil, and natural gas. Due to the discharge of carbon dioxide into the atmosphere, now 416 ppm of carbon dioxide is detected in the air. This results in the temperature increase. If we compare the temperature now and 1880, 2.1 degrees Celsius higher compared to the temperature in 1980. And Arctic ice decreased 13.1% every 10 years. And sea level is increasing, rising 3.4 millimeters a year. So this situation is not sustainable So many people concerned about this situation. United Nations proposed SDGs to create a sustainable society, and our mining sector also have to respond how to make the world sustainable. So I pick up two countries for these figures. So the upper one is the energy production and balance. Could you imagine which country have this chart? Oil, biofuel, and waste, wind, solar, etc. Very limited amount of nuclear and natural gas plus coal. This is Indonesia. So total production of energy is increasing. The lower one is different. We can see the decreasing trend of total energy, and the majority come from oil and natural gas and coal. And you can see nuclear power is dramatically decreased in recent years. So you could imagine this is a Japanese figure, because we had a big this problem of the tsunami that destroyed the nuclear power plants. So the government stopped the operation of all nuclear power plants in Japan, but now a few are revived. But anyway, the big problem of those countries and other countries in the world is still we depend on energy or power from oil and coal, and we have to decrease those ratios in future. So which source is our future energy? This is electricity production from crude oil, natural gas, and coal. And we can see an interesting trend. Those energy is increasing year by year until 2019, but dramatically start decreasing. This is due to the
recording in progress.
This is due to the pandemic of COVID-19, but I do not expect in near future this trend again change, again increasing, because many people try to diminish the usage of crude oil or natural gas or coal. Other sources we can see in the lower figures, nuclear, hydroelectricity, wind electricity, and solar panel. We can see a clear increasing trend, especially in hydro and wind and solar panel. So those are without doubt future energy. Nuclear is a question. For the Japanese, we don't think nuclear is a future energy because Japan is not a stable country in terms of the tectonic situation. Japan is facing the subduction zone and composed of very young geology, so it is not stable. Maybe the countries on the stable large continent, they can proceed a nuclear power plant, but not for Japan. So this is those are pictures of Akita Prefecture. Now there are lots of clean energy in Akita Prefecture. Tamagawa Dam, probably some students, even Indonesian students, visited there. And now we see a lot of wind turbines facing along the coast of Sea of Japan. And now those wind turbines are expanding into the sea. Also, we have several active volcanoes in Akita Prefecture. So geothermal energy is very important. And the photo shows Wasabizawa, the newest one. And we have another 3 ongoing projects. So we'll have more geothermal energy plants in near future. So this is a roadmap of global energy sector flagship report. And this is a quite ambitious plan, but IEA tried to reduce the CO2 discharge from several activities. For example, electricity and heat production, industry, or transportation building. And IEA aims to diminish and make it close to 0 by 2050. Japan also published a roadmap that is called Beyond Zero Carbon. And there are 3 purposes. One is to reduce greenhouse gas emission by 26% from 2013 levels by 2030, and promote the development of innovative technologies by 2050 that enable Japan to contribute the reduction in accumulated atmospheric CO2 globally to beyond zero. 3, the third purpose is to achieve net zero greenhouse gas emission by 2050. Anyway, those are quite ambitious aims, goals, but we try to make this possible. This is a new project by Jogbek. Jogbek is a governmental exploration company, and they used to develop oil, gas, and mineral resources. However, they completely changed their mind, and this is a new project they just started. They try to produce ammonium and hydrogen from the natural gas plants, and the CO2 produced during the production of those gases will be buried underground. That is called carbon capture and storage. Then ammonia and hydrogen is transported to Japan, and this will be used for power plant, hydrogen station, fuel battery, etc. The lower photo is a plant to be exported to Indonesia for the production of ammonia. So anyway, so world is changing very quickly, and I'm an economic geologist, and I'm studying mineral deposits. So from my view, some elements or some mineral deposits are very important to promote the production of clean energy. To produce solar panel, we need a silicon or cadmium and telluride, or copper, indium, gallium. For production of lithium-ion battery, lithium, cobalt, nickel, carbon, graphite are necessary. And to produce wind turbines, rare earth magnets are used. That include neodymium, praseodymium, terbium. Sorry, this is a mistake, and dysprosium. And electric vehicle also contain rare earth magnets in the motor and lithium-ion battery. Ammonium production, we need platinum group elements as catalyst. Then the many people expect the production amount of electric vehicle increase very quickly in coming 2 years, 10 years. So we need to supply, for example, lithium, graphite, nickel, cobalt, in addition to rare earth elements, more and more. This is again rare earth elements and expected electric vehicle sales number. We can see that is will be increased year by year exponentially, and we have to secure the raw material, rare earth element, for the production of magnet that is installed in electric vehicle and wind turbines. I show an example of the magnet that is called neodymium iron boron magnet that is composed of 70% of iron, 30% of neodymium, a few percent of dysprosium and boron. This magnet is very high in performance, probably more than 10 times stronger than the traditional ferrite magnet. Now, some of you may not know what is rare earth elements. This is a periodic table showing the rare earth elements in pink. Rare earth elements are a group of elements, including lantanoid. Atomic number is 57 is lanthanum, and N is 71 lutetium. Plus, we commonly add scandium and yttrium in the rare earth elements. So it is composed of 17 elements. And the element used for magnet is neodymium, or praseodymium, or terbium, or dysprosium. So those elements are very, very important. The production of rare earth elements are increasing exponentially because of the very strong demand year by year. This figure shows the rare earth elements produced by countries, and you can see from 2000 to 2010 or 11, the majority of rare earths were produced in China, but demand is more than the Chinese capacity. So now, in addition to China, USA, Australia, and other countries producing rare earth elements. This is an updated table showing the production and reserve of rare earth elements in the world. Still, China dominates the production. About 60% of rare earth is produced in China from carbonatite at Bayan Obo in northern China, and ion adsorption deposit in southern China, followed by United States. It produces 15 or 16% of rare earth element from mountain pass in that is carbonatite deposit. And very interestingly, the third is Myanmar. Myanmar is producing 12.5% of rare earth element now. It's mainly from the ion adsorption type deposit, similar to the one in southern China. So many countries now are producing rare earth elements: Australia, Madagascar, India, Russia, etc. Now I would like to briefly explain the geochemical behavior of rare elements. This figure shows the ionic radius as a horizontal axis and ionic charge as vertical axis. And we can see rare elements are plot around here, lutetium and lanthanum. But those elements generally have a +3 valence. So that is one higher compared to the iron or magnesium. And the ionic size is slightly larger than magnesium and iron. So rare earth elements are slightly, we call it incompatible compared to the incompatible against the minerals that contain iron and magnesium. So this incompatible characteristics, rare elements are enriched in the magma until the last stage. So if we compare the, for example, the rare composition concentration in oceanic crust and continental crust, rare elements are more enriched in continental crust because continental crust is made of mainly by granite. Especially light rare elements are more enriched because light rare elements are more bigger in ionic size compared to heavy rare elements. So light rare elements are more incompatible. So this is a very schematic figure, but showing the magma type and the degree of partial melting. If the degree of partial melting is smaller, incompatible elements are concentrated. So we are living in the subduction zone. So we see a lot of alkaline andesite or solite. The degree of partial melting is about 20%. But for example, carbonatite, degree of partial melting is less than 5% and sometimes 1%. So carbonatite, in carbonatite, rares can be more concentrated because of the incompatible characteristics. That's why several carbonatites become a rare deposit. And also alkaline basalt formed by lesser degree of partial melting compared to the degree that form the alkaline andesite. So alkaline basalt also can contain a slight elevated amount of rare elements. If we look at the minerals from which rare earth is produced, we can see several ones. Majority of rare earth elements are produced from bastonesite, rare earth carbonated mineral that is included in carbonatite. The monazite, rare earth phosphate mineral, this is also included in carbonatite and in addition to other type of deposits, such as placer deposit. The other ones are xenotime, nopalite, fergusonite, and kaolinite. The major rare deposit types are categorized into 4. One is carbonatite, that is formed by very low degree of partial melting of mantle material, and carbonatite mainly occur in rift zones. Generally, it contains a few percent of rare element. Alkaline rocks and alkaline granite also formed in a rift zone, relatively enriched in heavy rare elements compared to carbonatite. In some deposits, rare elements are concentrated as cumulated layers or fractionated part of the intrusive complex. Ion adsorption type deposit occur in weathering crust, similar to nickel laterite deposit, But in this case, the source material is rare earth-enriched igneous rocks, mainly granite. And rare earth elements are adsorbed on clay, kaolinite, and halloysite. Placer deposits, I think you are familiar with this type of deposit. Heavy minerals sought from rare element minerals, rich hinterland. Main ore minerals are monazite and xenotime, that occur with other heavy minerals like zircon or rutile or ilmenite in beach and fluvial sands. I'd like to show a few examples. This is a carbonatite rock at Mountain Pass in the United States. In the photo, we can see a light brown color part in front. This is a carbonatite. The sample is like this. This is very high in grade. So average grade is nearly 8% as rare earth oxide. So now the production of rare earth from the US depend on the production from this mine. Major ore minerals, if we look at the rock carefully, we can see a reddish brown mineral. This is bastonesite, rare earth carbonate, together with barite or calcite and other minerals. Alkaline rock, natural deposit, a very special deposit. It is quite a large intrusive complex, and that is very enriched in zirconium silicate minerals. So this intrusive cyanide contains zircon and eudialyte as magmatic minerals, but those minerals decomposed and secondary minerals occur. Those include fergusonite, magnetite, and albite. So in this complex, rare earth elements occur as a basal zone that is believed to form by cumulate. And this zone is very rich in heavy rare earth elements. If we look at the sample from this zone, we can see a lot of zircons. Those are zircons enclosed in phlogopite in this case. But this silicon is very high in rare earth elements, 3 to 14% of rare earth elements. But this silicon used to decompose into very minor zircons that is not rich in rare earth elements. But at the same time, we can see a light color mineral. This is a fergusonite. This fergusonite contains about 40% of rare earth elements. So during this decomposition, rare earth is transferred from zircon to fergusonite. So this fergusonite is the target of the exploitation. Ion adsorption type deposit. This is an important source of heavy rare earth elements that is formed in the weathered crust of rare earth element enriched granite. That is widely distributed in southern China. You can see red stars. Those are the sites of the mines. Generally, rare earth grade in this weathered material made of clay, kaolinite, is very low, 0.05% to 0.2%, but some are enriched in heavy rare earth elements, including dysprosium and terbium. And this material is free from radioactive elements, and the rare earth extraction is very easy. So developed mainly in southern China, but the mining site is shifting to other countries now. It's a little difficult to visit those mining places for foreigners, so we see the mining site by Google Earth, and we can see lots of open pit in southern China like this. And now Chinese miners extract rare earths by in situ leaching. They make a lot of holes on the surface and inject ammonium sulfate solution into the underground, and injected solution extract rare earth elements and finally recovered from the footfill of the around here. However, similar to the nickel laterite deposit, because this is recovered from the surface, we have to develop a very wide area for this leaching. Also, the grade is very low, so to produce enough amount of rare earth elements, the mining companies should develop a wider region. So that makes the natural environment that cause a very huge impact on natural environment. So even in China, this style of mining is not so welcomed. And now the main mining site shifted to Myanmar. This is an interesting Google Earth image. We can see a border between Myanmar and China, and I found a rare earth mining site on the Myanmar side, and I found a rare earth element refractory plant on the Chinese side. So probably the mined material is transported to this plant and produced as rare earth element. The last type of rare earth deposit is a pyrite deposit, a monazite. That is recovered with zircon and rutile or ilmenite as byproduct. So this is again still a good source of rare earth elements in some countries like India, Brazil, Malaysia, Vietnam. If we look at the distribution of pyrite deposits, that is worldwide. But if we look at the deposit with high monazite concentration, those are located in India, Madagascar, and Ceylon, etc. Anyway, that is a ancient boundary between the continents. New frontier. Some Japanese are very interested in the rare earth bearing mud in the Pacific, especially in the nearby the Japanese islands. That is called Minami Torishima. This is a deep sea mud from Minami Torishima, collected from the sea bottom, more than 5,000 meters in depth. And some layer of this mud contain elevated amount of rare earth elements, about 0.5%. It's very interesting. We checked the what minerals contain the rare earth in this mud, and we found apatite is a source of rare earth elements, and those apatite is very strangely looking. This is a image of apatite collected, and those are not the inorganic one, but probably fragments of fish bone, etc. So this is biogenic in origin. But anyway, this apatite contains about 2.5% of rare earth elements, and enriched in dysprosium or terbium, heavy rare earth element. So this could become a source of rare earth resource. But I'm proposing instead of developing a new mine, it's better to recover rare earth elements from apatite. Apatite is a material to produce fertilizer because it contains phosphorus. Because apatite occur in carbonatite, alkaline igneous rocks, and sedimentary rocks, we can see a distribution throughout the world. And some apatites, especially igneous in origin, contain 0.5 to 2% of rare earth elements. If we could extract rare earth from apatite, we can have a lot of advantage because apatite is has enormous resources, and this is a major product of phosphoric deposit, and so rare earth can be recovered as byproduct. And mineral separation is easy, and some enriched in heavy rare earth elements. And because apatite is very necessary to produce fertilizer, we can see a lot of active mining. This advantage is rare earth grade in apatite is relatively low. I would like to show one example. This is a Kibina per-alkaline complex in Russia. This is a very big igneous intrusive rocks, of which diameter is about 30 kilometers. And some part of the complex, we can see black in color, that is called apatitite. That contains 60 to 90% of apatite. And this apatite contains about 1% of rare earth oxide. So annually, several mines produce 9 to 10 million tons of apatite from this area. So that means 1% of the ore is a rare earth element. So this is a very good amount for the rare earth element if we could recover. So this is a general figure showing the process of fertilizer production from phosphate rock, apatite. So apatite is commonly dissolved with sulfuric acid and changed into ammonium phosphate, and finally used to produce nitrogen, phosphorus, potassium fertilizer. However, if we dissolve apatite with hydrogen sulfuric acid, we can have this reaction, apatite plus sulfuric acid, and we have phosphoric acid plus gypsum. So immediately we have the deposition of gypsum, and generally 80% of rare earth is included in this gypsum. So we cannot recover rare earth elements enough. So in our university, we tried to develop a method to recover rare earth from this apatite, and we found if we dissolve apatite with very diluted sulfuric acid, recovery reached more than 80%. So we propose to use this method for the extraction of rare earth element to the fertilizer companies. Unfortunately, until now, no companies try to use this method because fertilizer production is very good, so they don't want to produce rare sediments. But anyway, we have to change the world. We have to decrease the consumption of CO2 discharge into the air. So we have to develop new rare deposits. That is a little difficult. Of course, it is possible, but it also gives the large environmental footprint. So we are proposing rare elements recovery from apatite as byproduct, so that leave a smaller footprint for the environment, and we don't need to many mines. And finally, we will aim to recycle all the material to realize a sustainable society. My ambition plan is to produce this sustainable society for rare element by 2050. So that is similar to the Japan's beyond zero plan. Okay, thank you very much. Today's story is only for rare elements.
Yeah. Thank you very much, Professor Watanabe, for the interesting talk. So maybe we will move to the question and answer session from the audience. So we will have 5 until 10 minutes, yeah, for the question session. So does that have any question from the participant? Maybe you can raise your hand, or you can also text in the chat room, so we can discuss for the answer of that question.
Yeah, Susanti.
Yeah. Yeah, Prof. Milka.
Yeah, thank you very much. Thank you very much, Professor Watanabe, for very interesting topic for this discussion today. One make me interesting with one of your slide is regarding the RAA content, especially the apatite you get from your submarine samples. Yeah, this looks very interesting for me, especially the shape or the typical apatite minerals you obtain from the clay. Yes, looks like from the clay samples. I was wondering, is this sample taken was also related or nearly located with submarine like hydrothermal activity, or like a black smoker or white smoker nearby of the sample location area?
No, this is it's interesting. If we look at the result of the analysis, only layer mud in a limited layer contain high amount of rare elements. And one of the scientists is now dating those samples. And I have not heard the final result, but about those mud stone, those mud accumulated about 35 million years ago. So the seawater composition is not almost the same, and but changing time to time. And one probably the oxidation state of seawater was something different from the today's situation, and rare elements were highly involved in the seawater. Also, this rare composition is depleted in cerium. So cerium is a very the element responding to the oxidation state of water. So anyway, we had a very strange seawater composition at that time.
Okay.
Still, we don't know the exact composition of the seawater at that time.
So means it's not related with like submarine hydrothermal activity at the present, yeah, from these samples.
Might be.
Okay. Okay, thank you very much. And one last question, on your last slide, you also mentioned about the apatite, yeah, that can be used as a future energy, which can be recycle, yeah, this apatite. So, and also you mentioned that the apatite was obtained normally like from carbonatite, yeah. But my question is it also possible if we extract our apatite? For example, in phosphate minerals in Indonesia, mostly we have our phosphate minerals is like guano, yeah, from limestone. So do you think in that kind of phosphate mineral, we can obtain also a good result in apatite can be used as a part of this RE demand? Thank you.
Now, please check the composition, rare composition in apatite. Generally, sedimentary apatite contain a little amount of rare elements compared to those of igneous origin. And I checked some sedimentary apatite along the Red Sea in Egypt and Saudi Arabia, and those are enriched in heavy rare elements, but also enriched in uranium. So that was not so suitable for the production of rare elements. So we need to check the impurity in the apatite anyway.
Okay, thank you very much. Thank you, Bu Santi.
Yeah, thank you very much, Professor Mega, for the question. And maybe we'll move to the next question. If you have any question from the audience.
Okay. Any question?
So maybe for the student also can writing in the chat.
Okay, well, I can't understand that. I have a question. At the beginning, I explained a Japanese organization try to produce hydrogen and ammonium from the natural gas plant, and actually, practically one company is trying to export their plant to Indonesia. Do you have any idea in which part of Indonesia or in which company what company try to produce ammonium or hydrogen from natural gas?
I don't have any idea. Yeah, maybe here some Pak Rudi or Pak Kang Uun maybe can answer the question. I'm not familiar with this plan. Mungkin ada yang bisa bantu teman-teman dari Migas atau Kang Rudi. Ada yang tahu informasinya? Kang Uun mungkin ada, Kang Uun? Ini dari Pertamina. Itu Kang Uunnya masih di mute katanya. Pati panitia.
Okay,
I'm sorry.
It's okay. Well, this is quite interesting project, and I hope this will be realized in near future.
Yeah, hopefully, maybe. Itu Pak Wun tadi ada yang mau present disantik.
Ya, Prof. So the next is from Mr. Nugrahanto. Silakan Pak.
Yeah. Thank you very much, Prof. Mega and Prof. Watanabe. I actually would like to raise question, but not answering your question, Prof. I apologize. But for your information, that Pertamina is also try to do the hydrogen research, but I'm not familiar yet about that project because the project was handled by the other a group, yeah. So I currently work for the upstream, and then that kind of business is handled by the downstream business. But I will check it later and then inform Prof. Mega later if I had information. I do apologize, Prof. Watanabe, I cannot answer now.
Yeah, thank you very much.
Thank you, Pak. Okay, thank you. So, any more question from the audience?
Saya masih boleh bertanya?
Oh iya, silakan Pak.
Terima kasih, thank you. Prof. Watanabe, I have one question about the what is called the cooperation between the Indonesian government with Japan in terms of implementing the industrial sectors, yeah. Because what we discussed today is actually how to really understand about the rare earth elements, how to explore it, and then how to find it economically. But then, is there any agreement or cooperation in the GNG level, government levels between Japan and Indonesia that would like to be proceeded, like what Korea and South Korea already did the agreement with Indonesia through LG, building lithium battery factories in Bekasi, yeah, recently. So then, any rare earth elements in export and produce in Indonesia can be utilized directly inside the country. Is there any plan from Japan to also build some sort of industrial related to the rare earth elements, Prof? Thank you very much.
Okay, thank you very much for the question. Because rare earth elements are mainly included in carbonatite or alkaline rock or placer sediment or ion adsorption type deposit. I think it is Indonesia is not so promising compared to the other rare earth producing countries. Probably Indonesia is reaching nickel laterite deposit rather than ion adsorption type deposit. So Korea did a good cooperation, proposed good cooperation for the production of lithium-ion battery. However, one of my students from Papua New Guinea is now studying the placer sand in Papua Island, and he is finding an interesting result. So placer deposit might be interesting. But anyway, so far I don't know that any industry cooperative project between Japan and Indonesia in terms of rare earth elements. Some countries are very much interested in the Bangka Island because the placer deposits contain monazite and xenotime, so that could be a source of rare earth elements. Also, some companies were interested in the recovery of rare earth elements from the mining waste, and they did study, but that was about 10 years ago, and I have not heard about any progress about those projects.
Oke, thank you very much, Prof. Watanabe. Ibu moderator, terima kasih.
Baik, terima kasih Pak Nuganto. Oke, dari mahasiswa apakah masih ada yang ingin bertanya? Masih ada 1 menit. I think no more question ya, Sensei.
Okay.
So yeah.
Thank you very much.
Yeah, thank you very much, Professor Watanabe. So maybe we can conclude for the first topic today. That is about the rare element for the future energy, and also what is problem and recovery of rare element extraction from the apatite. So thank you very much, Professor Watanabe, for the interesting talk today. And I hope we can have another some kind of the webinar like this for the future operations. Thank you very much, Sensei.
Thank you very much.
Thank you very much, Sensei.
Thank you very much for Yasuse Watanabe. It is very beneficial to broaden our view related to this topic. Maybe for some participants, this is a new topic, I think. Okay, before we continue to the next speaker, we will share screen the video profile of Faculty of Geological Engineering. Please stay tuned.
Fakultas Teknik Geologi Universitas Pajajaran merupakan lembaga pendidikan tinggi yang menyelenggarakan dan mengelola 3 program studi, yaitu program sarjana dan program sarjana yang terdiri atas program master dan program doktor dengan didukung oleh 8 orang profesor dan 37 orang dosen sebagai staf mahasiswa. Fakultas Teknik Geologi dengan misi menjadi fakultas yang berstandar internasional dan bermanfaat bagi masyarakat. Salah satu tugas pokok dalam kurikulum teknik geologi adalah menciptakan lulusan yang memiliki keunggulan dalam kemampuan lapangan. Sehingga kurikulum teknik geologi dikembangkan secara terpadu dengan muatan sains penelitian, baik berupa pengetahuan, keterampilan maupun pengalaman penelitian dalam bidang geologi. Sehingga mahasiswa bebas memilih dengan outcome yang lebih baik sebagai bagian dari program merdeka pembelajaran.
Okay, ladies and gentlemen, the second speaker is Dr. Anjilian Ayura S. Gaburretio. She is from National Institute of Geological Science, University of the Philippines. Please to welcome Dr. Jillian. Today, she would be sharing with us about scandium and rare earth element in nickel laterite, insight from the Infanta deposit, South Palawan, Philippines, that will be guided by Dr. Santi. Dr. Santi, stage is yours.
Yeah, thank you very much, Ms. Aton. So, if in the first speaker we talk about the RIA in the general, so now we want to know about the such kind of the study in the Philippines. So it will be presented by Dr. Jillian Ayora Gaboracio with the topic in the scandium and RIA element in nickel laterite insight from the Infanta deposit, South Palawan, Philippines. So before we starting, I would like to introduce a little bit about Dr. Jillian. So Dr. Jillian was graduate from engineering in Earth Resource Science USU University with the research concentration on economic geology, especially in hydrothermal deposit, weathering deposit, and also in the sedimentary geochemistry. So if I saw in the CV, so many grant and awards from the international and national already got by Dr. Jillian, and also she has many training and development experience, especially in the United Kingdom, Taiwan, and also in the Kyoto University of Japan. So please welcome to our second keynote speaker. So Dr. Jillian, time is yours.
Thank you very much, Santi. So let me share my screen and start my presentation. So I hope my screen is okay. You can see it. All right. So thank you for the introduction, and I'm very happy to be here. Thank you for that. Well, to be with you. Even though I'm in the Philippines, thank you for the opportunity for me to be able to present our study on scandium and REE in nickel laterite. So this specific study is in Palawan, which is in the western portion of the Philippines, the one that is near Malaysia. And since you also have a lot of nickel laterite deposits in Indonesia, this might be something that might be interesting for you. So this study is a collaboration with our university and Kyushu University.
Recording stop. Recording in progress.
All right, so this will be the outline of my presentation, which will mostly focus on the behavior and characteristics of scandium and the other REEs, the yttrium and the lanthanides in nickel laterite. Okay. So as what Watanabe Sensei mentioned earlier, he did a very good introduction, so I won't dwell on that too much. But the rare earth elements are the scandium, yttrium, and the lanthanides. Okay, and as he mentioned earlier, they are used for a lot of green technology or new technology for batteries, for renewable energy. So it's really very in demand right now. However, the supply is a little bit critical. As he mentioned earlier, there are just several major deposits that can be mined for REE. And so some of the US and Europe has classified several REEs as critical metals. So in this regard, we should try to look for alternative or innovative sources of REEs. Okay, and one of that, what Watanabe Sensei mentioned earlier, is nickel laterite deposits. So nickel laterites, I think most of you know, are products of the weathering, tropical weathering of ultramafic rocks, mostly from ophiolite sequences. Okay, and the nickel laterites, when they weather, so from the bottom is the bedrock. Okay, and then above that is the rocky saprolite. And then further weathering is the earthy saprolite, and above that is the limonite, as shown here. Okay, so these nickel laterite deposits are the main sources of nickel, okay, and also iron. But it might be possible. We are trying to explore the possibility of extracting scandium and possibly other REEs from these nickel laterite deposits. So The Philippines, those in red are those that are the ophiolite complexes in the Philippines. So there are quite a few laterite deposits all over the Philippines. Okay, I will just highlight that in 2013 here in Palawan, the southern portion of Palawan, which is the westernmost island, which is very near Malaysia already, there is a scandium pilot plant, okay, and it was successful. So then what they did was they did it commercially. So they put up another processing plant in Surigao, this time in the eastern portion of the Philippines. So that is at present still operating, okay. It's at 7.5 tons of scandium oxalate per year, okay. So therefore, there really is some scandium that can be extracted from laterites in nickel laterites. So I think they said that the cutoff grade for scandium is around 55 ppm, okay, and they are still producing that at present. Okay, so the study area is very near the pilot plant. So the one in yellow star, that is the Infanta deposit, and that is what we will focus on for today. So our study wanted to know how scandium and other REEs are enriched during the process of laterization or during weathering. Okay, we want to examine where the REE is and where the scandium and where the REE is in the nickel laterite, and what could possibly have affected the deposition of scandium or the enrichment of scandium and the REEs. Okay, so to do that, what we did was we collected samples from surface exposures from open in the open pit. Also, we did test pitting and some drill hole samples. Okay, and although we did 1 meter interval, and the representative samples, we did petrography or microscopy and SEM-EDS and XRD. Also, we did mineralogy and also trace element, geochemistry, XRF, ICP-MS, and also we did LA ICP-MS on the samples. Okay. So the study area, zooming into southern Palawan, it's part of the Palawan ophiolite complex. So mostly it's ultramafic rocks and some sedimentary rocks. So the study area is mostly composed of Harshbergite with patches of dunite. So the orange in the map is the Harshbergite, and then you have your basaltic rocks, the pillow basalts. And then beside that is just your sandstone. Okay, so as you can see, TP4, 5, TP2, 3, TP1, DH1, those are the test pits and the drill holes where we got the samples. Okay. So when we look at the host rock, so first we look at the host rock, you can see that the mineralogy is your typical Harshbergite, olivine, orthopyroxene, then you have some spinels, okay, and you can see that the olivines and some orthopyroxenes are already serpentinized, okay, and so the composition is expectedly similar to your ultramafic rocks, so silica, magnesium, aluminum, iron, okay, and if you can observe, the scandium is very, very low. It's only 6 parts per million, while the other REEs are only 1.39 parts per million. Okay, when we look at the mineralogy of the nickel laterite, you can see that from the bottom, so the bottom part here is around 7.5 meters. The bottom part is mostly your silica and magnesium, which is from your olivine and pyroxene and serpentine. Okay, but as you move towards the top of the laterite profile, then you start seeing a lot of aluminum and iron oxide, especially iron oxide. So most of the iron oxide or iron hydroxides are classified as goethite, although some of them are amorphous phases of iron. Okay, and then some are so the yellow, the white ones here in the sample, they are your talc and your kaolinite, And then the green portions, they are the nickel rich portions. They are your garnierite. Okay. And if you can see the hand sample here, there are a lot of, so the iron hydroxide, the red ones, they have a lot of some veins. So they are your manganese, sort of manganese veining. Okay. So those are the main minerals that are found, that we were able to identify. Okay. Looking at the geochemistry, we see there is a very, very clear correlation between scandium and your iron oxide. Okay. So, and also with scandium and your aluminum oxide. And here, the top of the profile, your limonites, they have the highest scandium and also they have the highest iron oxide. So there's a clear relationship with scandium and your iron oxide and aluminum. However, these are nickel laterite deposits, so we tried to look for the relationship of your scandium with the nickel, but there doesn't seem to be any good correlation with the nickel. Okay. But as you can see, scandium is still present throughout the profile. It's just that the limonite zone has the highest scandium concentration. Okay. Looking at, so these are LA-ICP-MS ablation lines. Okay, so this is the sample that this is a polished mount of the laterite. So what we did was we ran ablation lines throughout different phases to try to see their relationship, the relationship of the elements with each other. So for example, here in the limonite zone, you can see a section where there is an increase, or for example, if you look at the iron, the one in light green, green-yellow, so there is a decrease in the amount of iron here. So that represents a separate phase. And then again, the increase, that is another phase. Okay, so we can see that aluminum and iron, and here nickel, and also your scandium behave similarly. Okay, your magnesium behaves the opposite way. Okay, if we look at the saprolite, we can see your iron and aluminum here in purple and blue. They behave very similar. And if we look at the scandium here below, the blue-green color, it behaves very similarly to iron and aluminum. However, the silica and the magnesium, they behave opposite, or sometimes or they behave in the opposite way. Okay, so what do we deduce from that is that probably the scandium is very closely related to the iron and the aluminum. Okay, so scandium replaces part of the iron, okay, in the pyroxene amphibole group, and during weathering, it precipitates along with the iron and the aluminum. So it is concentrated in the iron-rich parts of the laterite profile. Okay, so the goethite and the amorphous iron phases, those that are produced from the weathering of the laterite, they capture the scandium during laterization. Okay, so the nickel-rich portion doesn't have that much scandium. Okay, but it's still they still contain scandium, but not that high. So the low-grade nickel, which is the iron-rich portion, they contain more scandium. Okay. So that's for scandium. And looking at the other REEs, yttrium plus the lanthanides, okay, we cannot see a clear correlation with iron, with nickel or aluminum. It's not so clear. Okay, so probably the behavior of scandium and with the other REEs, they are very different. Okay, no relationship with iron or aluminum or nickel. So they are probably not related to the weathering process. So what do we see instead is that the REEs are concentrated in certain depths. So we termed it here as a pocket, REE pocket. So here you see this is normalized to thorium since they are stable under acidic conditions. And you can see at depths of 6 to 8 meters, the REEs, especially the MREEs, are high, okay, a little bit high. But although the LREs are not so high, but in any case, they are just concentrated in a specific area. So looking more into this, we noticed that the cerium anomaly changes, okay? At shallower depths, the CE anomaly is positive. But at lower depths, the CE anomaly becomes negative. And in the area where you have the reversal of this CE anomaly, that is where you have your enrichment of REE. Okay, and probably this represents the oxic environment from CE3 plus to CE4 plus. Okay, so is the border of the cerium anomaly related to RE enrichment? We tried to look at other profiles, okay, and it's still the same. So it's a positive anomaly above or in the shallower portions, and then below is a negative anomaly, and in that boundary is where you have the enrichment of your REEs. Okay, it's in the transition zone between the limonite or the iron-rich zone and the saprolite, which is the nickel-rich zone, probably reflecting the change in pH or oxidizing conditions, which can be because the limonite zone and the saprolite zone is the boundary of the paleo groundwater table. So that could be the reason. And that is where your REEs are concentrated. Okay. Looking at other elements, we noticed that the manganese also has good correlation with these other REEs. Where there is an increase in manganese in the profile, there is also an increase in the REEs. Okay, so when we look at the LAICPMS results, here you see the manganese and the cobalt. They are somehow similar to a little bit similar to your other REE. So they behave at least similarly. Okay. So the behavior of the other REEs, so your lanthanides and your yttrium, they are different from the scandium. And anyway, scandium is more abundant. Okay, but the REEs are just up to 60 parts per million. They are found in two instances: the border of the CE anomaly, which is also the transition between the limonite zone and the saprolite zone. Okay, and then they're also correlated with the abundance of manganese in certain portions of the laterite profile. So probably manganese are good adsorbents of your REEs. So to conclude, the scandium is concentrated mostly in the limonite profile, the iron-rich layer. Its formation is very much associated with the formation of your iron hydroxides. Okay? And the scandium can be or is already being extracted as a byproduct of this limonite zone. Okay. However, the REEs, they are in much lower concentrations, around 60 ppm, but they are found in just specific layers. So in the boundary between the limonite zone and the saprolite zone, in that transition zone is where you find your other REEs. While in other instances where you have increase in manganese, you also have increase in your REEs. So the REEs only accumulate at certain depths, probably where you have change in certain formational conditions. Okay, so I only have a very short talk compared to Watanabe Sensei, but I hope somehow you got something from the presentation. Terima kasih.
Yeah, thank you very much, Dr. Jill. We are really thank you for your talking, because yeah, during your field work you still have time, yeah, to give a short talk about a case study in the Philippines. So maybe we will continue with the question from the audience. So any question? Yeah, maybe from Pak Agus Didit, related with the mineral and RAA.
Okay, Dr. Santi.
Ya, oke, Bu Aton, silakan.
Yeah, thank you very much. Thank you, Dr. Julian. This topic is very interesting because the nickel laterite is also can be found in our country, especially in eastern of Indonesia. If I see that your explanation that scandium related to low grade nickel laterite, yes, okay. Now, as far as I know, that nickel laterite in Indonesia generally found in the dunite rocks. It's originally from dunite rocks, yes, and it has abundance of magnesium rich, then very rich, yes. So I would like to ask, is host rock of the nickel laterite is affected to the abundance of the scandium? That's the first question.
Okay.
And the second question, yeah, nickel laterite is originally from the ultra basic rock. As I know that ultra basic rock is originally either a mantle or subduction process. Which one? The scandium high value from if we look at the tectonic setting like that. Thank you very much.
Okay, thank you for your question. So actually at present, we are still trying to compare the different host rocks, Harshbergite, dunite, or Lherzolite. But based on our initial results, the more pyroxene there is in the mineralogy, the higher the scandium. So the source of the scandium is in the pyroxenes. So if it's dunite, probably it will have a little less lower grade, but the Lherzolite we expect to have probably higher grade. Okay, but we are still in the process of comparing everything. But because we know that the scandium is related to the pyroxene, so we just look at the mineralogy, the more pyroxene there is, probably the higher the grade of the scandium. Okay, and then looking at the tectonic setting, it's mostly related to the mantle, because the Lherzolite is the primitive mantle rock, right? And then you have your Harshbergite. So the more the mantle rich or the mantle setting is where we expect to have more scandium for your nickel laterites. If it's a little more basic, like your basalts, usually we get the bauxite already, or the aluminum rich portion.
Okay, thank you very much, Dr. Gil.
Yeah, okay. Any more question, Bu Aton?
Pak Agus is raising his hand.
Yeah, Pak Agus did it.
Okay, thank you. Thank you very much, Dr. Jill. I have a small question. I think is as you mentioned before, the scandium not related to pyroxene and olefin, right? The mineralogy, and then as your result in your research is there is a widespread from any rock, both of Harshbergite and so on. So I just want to know, have you done collect the sample from a selective rock, a selective mineral from maybe Has Bukit, some rock. So I mean, this is olivine or pyroxene from the special rock. I think maybe there is you can compare between maybe
Yeah.
like that.
Yes, thank you for that. Actually, we are just about to do that. We have samples for EPMA analysis. So that is the next step. But we haven't gotten to it yet because of the lockdowns. But
Okay.
yes, that's what we want to do next. Thank you very much.
Okay. Thank you.
Yeah.
Maybe maybe you have some hypothesis, something like that. Which one's the big factor for oh, there is the scandium is maybe in
Yeah, so just our hypothesis is the scandium came from the pyroxene. So we are probably going to look more into the pyroxenes.
okay. Okay, thank you Bu Santi.
Yeah, thank you Pak Agus Didit. Maybe for the next question is from Mr. Nugrahanto. Silakan Pak.
Terima kasih Ibu Moderator. Hi, Dr. Jill. I'm Kuntadi. I have questions about, I think when I listened to the presentations from someone came from the other countries, I think first thing is how we can learn it from that countries. And Philippines is really amazing in studying about geothermal and then a lot of things about the petrology. I'm just curious about the potential resource of the scandium, for example, in Philippines. How big is it? So then you are interested in this research because at the beginning that the moderator said that you studied about the economic geology. So I think Indonesia would like to also learn how to make most of those what is called petrology related kind of resource can be economics in Indonesia, because Indonesia is so big countries. It is difficult to make a focus on and such thing, but then amazing that Philippines is one of the country that utilizing the geothermal. I think is the largest geothermal energy usage in the world. I think when I attended one of the lecture from my professor. Yeah, I think that's really the most question. How big is actually the scandium potential resource of Philippines? So then Philippines can probably make money from that. Thank you.
Thank you very much for your question. But actually, it's only because there is a pilot plant that was constructed by the Japanese. That is why we had an idea that you can extract scandium. But what we do mostly here in the Philippines is just direct shipping of our nickel laterite. We ship it to China. Okay, so that's why we are trying to study the possibility for scandium and other REEs, so that probably the other nickel laterite mining companies can be enticed to do processing here in the country. So actually, it's our study, and also I think Watanabe Sensei's study by his students. They are the only studies that focus on scandium here in nickel laterite deposits. So I think in that aspect, I cannot answer specifically how much the scandium is, but I can say that where there is the nickel laterite deposit, we somehow are sure that there is a scandium resource as well. But it's a matter of, are we just going to sell it to China, or are we going to process the scandium? So that is the problem. But also, I would like to point out that at present, I think in 2018 or 2019, Indonesia already surpassed the Philippines for geothermal energy production. So we are now third. US is first. Indonesia is second, and we are now third.
Thank you very much. I
Good
think,
job to you as well.
yeah, I think we are leisure because we have a larger area. So I think it's just still amazing that Philippines can still utilize all of those limited resources for your country. Anyway, thank you very much. Appreciate your question, your answer. Thank you
Thank
very
you
much.
very much.
Yeah, thank you very much, Dr. Jill. Maybe from audience, any more question?
Boleh saya, Bu Santi.
Yeah.
Yeah.
Silakan.
Thank you very much, Jill, for the very interesting talk. Yeah, it's some inspired to us regarding this study. Yeah, and also in Philippines, you have already a pilot plan with this scandium. I was wondering, as you mentioned in your presentation, mostly the scandium is concentrated highly in the upper part. Yeah, the upper part in iron, associated with the iron. Yeah, how they can I don't know, maybe this is some kind of the metallurgies later on. You can separate later on this scandium with the iron, because the layer is a high iron concentration, yeah, and also maybe some silica also accumulated also in that case. Do you have any exercise with that?
So actually what they do is high pressure acid leaching. So first they extract the iron, and then second pass they extract the scandium. So that is the process is very secret. They're very secretive. So it's a little bit of a secret, but that is all we know, that they do HPAL. And then they extract the iron first, and then the next pass of the same sample, they extract the scandium.
Okay. And in your profile also you mentioned in certain depth from your drilling data, there's some accumulation of this scandium is only in several layers, yes, not on the whole layer. And in some, I saw in the figure also is associated with some RAE, yeah. But you show also in the figure, you have any direct relationship within this scandium and RE?
So the scandium, it's still present even up to the saprolite, although at lower concentration. But it's really separate, the relationship of the scandium with the other REE. So it seems that the scandium is going with the iron and the aluminum, but the other REEs, they are going with the manganese, and also where there is a change in oxidizing conditions. So for now, I cannot say if there is a relationship between scandium and the other REEs, just that scandium goes with iron during the weathering process, but the REEs, they are present where there is the change in oxidation.
And do you think also we can still obtain this scandium from the host rock?
In the host rock, it's very, very low, 6 ppm. Okay. And according to the plant, their cutoff grade is 55 ppm. So, and that only occurs in the limonite layer or the upper layer. So maybe in the host rock, it's too low.
Okay, it looks very interesting, because now I have our student who start to looking for this scandium in some of the nickel laterite in some concession in Indonesia. Thank you very much for this insight. Yeah, give some idea for us also to study more in detail with this. Thank you very much.
Yes, thank you very much,
Mega. Yeah, maybe I think no more question from the student, Dr. Jill. So we would like to say thanks again to your talking today, and that is a really interesting talk for us, and we can study more about scandium from your country. So we hope our fruitful collaboration will continue. So once again, thank you very much for your time, Dr. Jill.
Bu Santi, masih ada tuh yang nanya di chat.
There's another question.
Yeah, on the chat, yeah.
So from the Ikrar Mandiri, so you have mentioned that the scandium originated from the pyroxene. How about the INLN in the occurred in the any contact between limonite and saprophyte at any laterite?
Okay, thank you for the question. So the problem is that the yttrium and the lanthanides, they're very low concentration, so less than 60 ppm. That is why we cannot really detect where they are specifically in the layer. So we will be doing the EPMA so that we will know the specific minerals where you find the high REE. But at present, we can only say that they are in that area because of the geochem results, but they are still very low concentration, so it's very hard to detect where they came from. Thank you.
Thank you, Dr. Jill. So, Mr. Ikrar, any more question? Is that clear for you? Okay, thank you. So maybe all of the question, Dr. Jill. So yeah, thanks again for the today presenter. And yeah, we will sending the certificate to you. Maybe I will send by email later. So yeah, thank you very much for your time.
Thank you very much, everyone. Terima kasih.
Terima
Thank you,
kasih.
Jill. Terima kasih.
Okay, thank you, Dr. Jill. It is a very interesting topic. Yeah, I think it's possibly can be applied in our country, especially in Sulawesi, yes, because there's the silent lot of nickel laterite. Yeah, before we come to the last speaker, please see the video profile on Faculty of Geological Engineering. Please stay tuned.
Fakultas Teknik Geologi Universitas Pajajaran merupakan lembaga pendidikan tinggi yang menyelenggarakan dan mengelola 3 program studi, yaitu program sarjana dan program sarjana yang terdiri atas program master dan program doktor dengan didukung oleh 8 orang profesor dan 37 orang dosen sebagai staf mahasiswa. Fakultas Teknik Geologi dengan misi menjadi fakultas yang berstandar internasional dan bermanfaat bagi masyarakat. Salah satu tugas pokok dalam kurikulum teknik geologi adalah menciptakan lulusan yang memiliki keunggulan dalam pembuatan lapangan, sehingga kurikulum teknik geologi dikembangkan secara terpadu dengan muatan sains penelitian, baik berupa pengetahuan, keterampilan maupun pengalaman penelitian dalam bidang geologi, sehingga mahasiswa bebas memilih dengan outcome yang baik sebagai bagian dari program merdeka pembelajaran.
Ladies and gentlemen, the third speaker today is Dr. Abhisit Salam. Please to welcome Dr. Abhisit. He is from the Department of Geology, Faculty of Science, Chulalongkorn University, Thailand. He would like to deliver mineral related to mineral deposits of Southeast Asia. This session will be guided by Dr. Santi as well. This session is yours, Dr. Santi.
Yeah, thank you, Ms. Aton. So thank you very much, Dr. Abhisit Salam, for today. Attends our webinar and as our keynote speaker for the third session. So before that, I would like to introduce a little bit about our keynote. So Dr. Abhisit Salam is from Chulalongkorn University with education background is from University of Tasmania, Australia. And for the industrial experience, Dr. Abhisit Salam has been Eureka exploration for industrial mineral and granite and marble, and also in the Akara Mining Limited, or now is Akara Resource Public Company Limited, to be exploration and mining for gold. And for the academic background, Dr. Abhisit Salam was a research fellow at CODES, University of Tasmania, with the topic research on the Southeast Asia or deposit project, and also now is a lecturer at the Department of Geology, Faculty of Science, Chulalongkorn University, Thailand. So please welcome to our keynote speaker, Dr. Abhisit Salam. Time is yours.
Thank you very much for having me. You please share screen.
Yes, doctor.
So, okay. Okay. Can you see the screen now?
Not yet, doctor.
Okay, so that's last slide. Okay, so again, thank you very much for having me here. And Assalamualaikum. So I'll start the talk today. Actually, I found out that the topic, the other talk is related to rare earth elements. So my focus will be separately, will be different. So I think it's maybe useful for you, for all participants. Therefore, I introduce about the mineral deposit of Southeast Asia. And at the end, I also talk about the lithium exploration in southern Thailand. And it's not much about lithium at the moment. At least only one exploration is going on in southern Thailand. And okay, so I'll have start from the first.
Sorry, Dr. Abhisit Salam. We are not yet show your PowerPoint.
Okay, you cannot see your my screen.
Yeah.
So sorry, it's technical problem. Okay.
Yeah.
Can you see screen now?
Yes, doctor.
Okay, sorry, yeah. Okay. For size. Sorry. Again. Annotation. Just a second, yeah. Okay, there. Okay. That should be okay. Okay, today I will talk about the mineral deposit of Southeast Asia. And the outline of the talk will be Southeast Asia major mineral belts and major mineral belt of Southeast Asia mainland, and characteristic of some mineral deposit in Southeast Asia. And lastly, we'll talk about the lithium exploration in Thailand. And Southeast Asia mineral deposits are of several types and broadly occur into tectonic environments. First is convergence related or subduction related, Another one is the rifting environments. Sorry, this one is the subduction related. Then you can have also the porphyry type of deposit, epithermal skarn, which is the major deposit in Southeast Asia. Another one we have here, which is continental rift zone. That is sedimentary hosted. And copper, gold, and tin tungsten, which occur in the first type of tectonic setting. And the rifting zone prefer lead zinc deposit mainly. And here is the major mineral belts in Southeast Asia. But I'll focus on the Southeast Asia mainlands instead. As we know that Indonesia and Philippines have several of deposits, and most of the audience are from the Indonesia, so I'll skip the Indonesia and Philippines just for focus on the Southeast Asia mainlands. From here, we can see that gold actually in the China, South China, and lead zinc, silver mainly occur in the Myanmar, East Myanmar, in Chan State, and also some of them in Western Thailand. And third one is copper gold in green, that also found in the Myanmar and also in the Thailand in Loei Four Belt, which is one of them is a Chatri epithermal gold deposit located here. And the rest, as I say, mainly in the Indonesia and Philippines. And the fourth one is the copper gold moly. This is quite different. You have moly associated with this belt. This belt in South China, but in Southeast Asia mainland, this belt are located in the Laos mainly, extend partly into the Vietnam, and also may probably extend to north of Cambodia. And another one is tin tungsten. So I think all of us familiar with tin tungsten belt of Southeast Asia. This belt started from Eastern Myanmar to Western Thailand and further down to the Peninsula Malaysia and end up in the Belitung Island in Indonesia. Another small belt also currently I established here in the Eastern Thailand and extend further to the Malaysia. This one is dominated by antimony and also associated with gold. So gold with antimony, different from gold in the this part of the belt and also in the gold copper one. That one doesn't have antimony. And this belt consists of numerous commodity and various styles of mineralization. Many of these belts are overlapping. For example, copper gold overlapped by zinc, lead, silver style deposit. The overlapping is generally related to deposit of different age, associated with different magmatism or different tectonic setting. So we can expect different community in the same belt. Let's start with copper gold and the green one. So copper gold is typically related to ancient and modern plate margin. And some of them are major world-class deposit, especially in Myanmar. We have porphyry deposit, Moniwa deposit in Myanmar, that also world-class. And also Chatri is epithermal deposit, is considered to be medium size of deposit. And other deposit in Laos also, Pukam, Skarn, also relatively big size as well. And now we look at the porphyry, high saturation, epithermal, and Skarn. So this kind of combination we have in the Loei Four Belt and here Leuphor belt. And example of this deposit is the Putafa, and the porphyry style do occur in this belt, but mostly up to now is sub-economic. And the other one is in the Indonesia. So that is, we all know about that is Sunda Banda Mata Bay and Tunjung Bukit, Indonesia. So I will not talk about detail of that. And another one is low sulfidation epithermal. And this one is located in the Thailand, in Leuphor belt. Chatri is one of the example. And for tin tungsten, one of the world important tin tungsten belt. So this belt is considered is one of the world tin producing area in the past, 30 years ago. Myanmar and Thailand, Malaysia to Sumatra. The extension is start from Myanmar to Thailand, Malaysia, and Sumatra. Mainly, the deposits are classified as alluvial type. Minor primary deposit, mainly skarn. For example, in Takua Pitong in Western Thailand, and currently produced mine in Mauchi. This one is one of the world's biggest tin tungsten deposit, and now also still operation. And small deposit in Thailand also still operation, and that one is in northern Thailand. The deposit name is Samburg deposit. And for zinc, lead, silver deposit, the belt in gray color, as I say, is actually extend from the South China to Eastern Myanmar, and some of them also in the Western Thailand. So these deposits are various style of and belt. Some of them occur as a VHMS. For example, in Batwin in Myanmar, this one still operate and considered is one of the big deposit as well. And Semao Bell Da Pinchang in China. And for sedimentary hosted deposit, example is the Mesot and Song Tho in Thailand. These two deposits has already mined out, but Mesot is a famous one. It has been mined for 30 years, just only mined out for last few years only. So another one is the recent discovery in the Deri in Sumatra and Qingding in China. And for copper gold moly deposit, so the belt is the Trung Song Pho belt, mainly in the Laos and part of the Vietnam, and probably extend to north of the Cambodia. So this Trung Song Pho belt, copper gold moly. A good example is Phu Kham, which form as a skarn deposit. And Ban Huay Sai deposit occur as a low sulfidation epithermal gold. And for KSO in Laos, this one classified as orogenic gold. And Sepon occur as a skarn, as well as the sedimentary hosted. Phuc Son in Vietnam classified as intrusion related, and as well as vermeil. And most of the deposits are still under operation. And a bit more detail on Myanmar. So this part, and in Myanmar, major deposit are Chao Patho. Chao Patho is epithermal deposit. It's here. Chao Patho is epithermal gold deposit. And Mori Town its original gold now has been terminated. So Morita is here. And for copper is Moniwa. Moniwa is occur as porphyry, but some article classify as high sulfidation epithermal deposit. So it's not clear that. And this is Moniwa in central Myanmar. And the other one is for lead zinc. Budwin is a lead zinc deposit hosted in the sedimentary rock. Budwin is here. So Budwin in the Chan state. And for tin and sandstone, it still operate is a multi-area now. It's still not currently considered as the world biggest mining for tin tungsten. Now we move to the Indochina area. So here we have two mineral belts. One is Trung Song Four Belt, and another one is the Loi Four Belt. So the Trung Song Four Belt I associate with about 300 million years of volcano-plutonic belt. So basically associate with volcanic rock and plutonic rock about 300 million years, so Carboniferous. And relative younger at in Loi Four Belt. This one associate about 250 million years of volcanic and plutonic rocks. And the occurrence of copper gold deposit is confined into three major regions for the Trung Song Four Belt. One is here is the Phubia deposit. So Phubia deposit is constitute about 1 million copper reserve at 4.2 million ounces of gold. And at Sepon, which is in central part, contain about 2 metric ton copper and 4.8 million ounces of gold. And in central Vietnam, here, this one from both Phuc Son and Bao Miêu mine consists about 0.7 million ounces of gold. Another one also originate gold, located somewhere around here, outside this major area. And this one intrusion-related gold deposit. So, and this belt extend further to northern part of Cambodia in Ratanakiri province, where porphyry mineralization has been reported recently. So for Thailand and Malaysia, as earlier I said that this one is a Loi Four Belt. So Thailand has the major mineralization, mineral deposit are confined into Loi Four Belt. And the important mine are Putapha here, and currently had been terminated due to the environmental issue. And second one is Chatri deposit, and this one also has been terminated in last few years. And another one is here is a French mine. French mine occur as a scan, but this mine out for many years ago. Another one is interesting is in the Sukhothai Four Belt. And here is the gold occur with antimony. And another prospect here is Botong prospect. Gold also associated with antimony as well. If you look down into Malaysia, several deposits located in this continuous region of the Sukhothai Four Belt also has similar commodity. So gold is also associated with antimony. So probably this belt has the antimony as the major commodity with byproducts of gold. So if you use these two commodities to define the tectonic setting, probably it's different from this Leupold belt, which is mainly gold and copper and as a main commodity. And the last part of the talks, I'll talk about lithium exploration in Thailand. As I say from the beginning, the information of lithium exploration in Southeast Asia, including Thailand, are very limited. But at least one exploration has been active at the moment in Thailand. So basically, the lithium deposit in this region is confined into the thin tungsten belt. So this, as we know that this thin belt extends into also Indonesia. Sorry, I think the belt may be incorrectly drawing. The belt should be going to this one, to Belitung Island. So I'm sorry for that. So in Indonesia also, we might expect that lithium deposit can be also found in the Belitung Island as well. So the lithium deposit in this belt occur in pegmatite dike, may or may not hosted in granite. The prospect undergoing now, the lithium bearing pegmatite is hosted in the sandstone, so it's not necessarily hosted in granite as we thought. So in Thailand, currently explore going on at Phang province near Phuket area. So another prospect also in the Myanmar has been reported as well. So that prospect is the Thasi prospect located in Heliang Det area in the Meltila district, known as the main feldspar producing area in central Myanmar. So because of no detail for this, now I'll focus on the southern Thailand prospect. And here in the Phang, as you can see from this slides, the prospect is located in the Phang. Here is a Phuket area, Phuket province. And the project includes two main prospects. One is the Reungkit prospect. Another one here is the Ban Ai Tung prospect. And currently, the company also explore geothermal lithium, as well as in hard rock lithium bearing granite in the nearby area as well. So that this also may be a future for exploration as well. Here, zooming to see that this is the Ban Ai Tung prospect. This is the trending of the pegmatite. Another one is this Reungkit prospect. The pegmatite bearing the lithium also has a similar trend, northeast southwest. And at both prospects, okay. And this zoning of the potential area is based on the soil geochemistry, soil probably also the rock chip sample. Here we look at the few outcrop of this. On the left is pegmatite vein or pegmatite dike hosted in sandstone, and this figure shows the the pegmatite is similar to normal pegmatite. It consists of mainly quartz and feldspar. So we can't see the lepidolite here. Another figure also just to zoom to show the quartz and feldspar mainly. The difference of the lithium-bearing pegmatite from the normal pegmatite is the presence of lepidolite minerals. So if we look at for the lithium potential pegmatite, we have to look at the lepidolite mineral. And here to show the potential area for prospect at the Römkiet. So the only one example I give here. And here this the red zone represent of the potential area for lithium mining. So the green square it represent the rock chip and the soil sample. The average grade is about here, particularly, it's almost 2% of lithium oxide. So in general, in this red zone, it's more than 1% of lithium oxide. And the red area show high concentration of lithium oxide based on rock chip and soil sample. And these two drill hole, diamond drill hole, and I'll show this cross section in the next slides. So one of the drill core sample, they drill up to the 95 meter depth, and this represent the pegmatite vein or pegmatite dike, and it contains series of dike, and hosted in sandstone instead of granite. And so for this particular case, it needs several pegmatite dike in order to make it economics. Based on the weathering profile or weathering profile, at this area, the weathering is quite deep. So this might be help in terms of the production cost, mining production cost. This is an example. These are example of the drill core to show you. The dark color is a sandstone host rock, and the light color is the pegmatite. And the next slide is thin section photomicrograph of this pegmatite. As we can see here, it constitutes mainly of quartz and feldspar. Feldspar are not identified in this image, and the rest is here is lepidolite and plain porolite, also the same area. And the important is the presence of lepidolite or lithium-bearing mineral. So if we, in terms of exploration, if we look at lithium bearing pegmatite, we need to find out the lepidolite or lithium bearing minerals. And the key exploration is very simple. First, to look at the pegmatite dike, and then we can do the petrographic study to look at the lepidolite to distinguish from those of the common pegmatite, which is very common in this region, and then follow up by soil and rock chip sample and for analysis. Once we get this result, if it is potential or significant anomaly, then we probably can put the diamond drill core to test the potential area. That is the key for exploration. that is for my talk today. Thank you very much.
Okay, thank you very much for Dr. Abisit for your sharing the experience and your knowledge. Now it's time to discussion. Maybe the audience have the question can be written in the chat room or asked directly.
Boleh Bu Atan?
Ya, silakan Prof.
Yeah. Thank you, Dr. Masyu, for the very interesting presentation regarding this South Asian belt, and of course the final presentation related with the lithium prospect and deposit. I have two questions related with this South Asian belt. On your presentation, you mentioned the Sukhothai belt in Thailand is mostly you mentioned, but you also said that this belt is possibly continue. This belt is also possibly continue to Malaysian area belt. But in your presentation that you mentioned in Malaysia, this continuous belt is mostly they found deposit gold is quite different. As in your side is mostly epithermal deposit, but in Malaysian side mostly is an orogenic type deposit. What happened with this? Is it still same continuous belt or some different belt within this Thailand and this Malaysian belt? Thank you.
Okay, it is a good question. Yes, I think it's the. If we look at the tectonic setting, this the Sukhothai belt probably extend to Malaysia, and but the mineral deposit, I try to constrain the tectonic belt using the minerals deposit. As we know that the Leipo belt it contain only the gold, copper, and iron, and this one is if we look at from the northern Thailand. We have to Malaysia, and surprisingly, we have antimony as the main commodity. But we do have also gold, because gold is the high price. The people mining for gold, not for antimony. And I have opportunity to do also research in Selensing in Malaysia. And first, they don't report the antimony, but when I did, I found antimony. And if we look at paragenesis, all are same, whether in northern Thailand and in Malaysia, we have the paragenesis, you have arsenopyrite bearing vein, and then you have the base metal bearing vein, and then you have gold veins. And finally, you tend to have antimony. So using this, although in Indonesia, in Malaysia, you have metamorphose, but very low grade. So that's why they define as the orogenic gold based on the metamorphic. But in Thailand, also not clear because not many study there. But I think is we can define as a continuation. Thank you.
Okay. So means that we can say that the one in Malaysia is called as orogenic, maybe in epigonal side, the upper part of the orogenic, which is quite almost similar with epithermal characteristic. Yes. So that's why maybe people can say it almost similar and continues the belt.
Yes.
And one more question regarding the lithium. You mentioned about the lithium oxide. You get it in granite, altered or weathered granite. But also you mentioned that the possibility of getting this lithium prospect or deposit based on or from the pegmatite dike, pegmatite dike without the weather. So means we can obtain this two. One is from weathered granite, and the other one is still primary pegmatite. We can expect to get the potential for this lithium, especially in lepidolite for dike of the pegmatite.
Yes, but so far in southern Thailand, in Phang Nga or around the Phuket area, they explore in the pegmatite. I think first idea is they look at for the thin tungsten mining, the ore mine. But they found that this pegmatite is located outside the granite, so hosted in sediment. And the pegmatite has the lepidolite. That's why it gives the lithium resources. And but they do also explore in the granite. Some granite also, the report says some granite also has a significant concentration of the lithium. And besides that, they also explore into prospect in geothermal. And one of them, they currently produce energy from geothermal. So it also contains significant concentration of the lithium as well. So in summary, there is a chance to find lithium in the pegmatite, directly pegmatite, and also in the granite, certain type of granite, and also the geothermal that might be related to granite. Thank you.
Okay, thank you. Thank you for the explanation.
Okay, thank you, Dr. Professor Mida Fatima Besana. And our next question from Ikrar Mandiri. First, what method is the most economic for lithium extraction from lepidolite? And the second question, what is the cutoff grade of the lithium that economic to be mined using recent extraction method?
I have to say that, thank you, first of all, but I have to say that so far I haven't involved in the study of the extraction of the lithium, but maybe I'll continue after this. And for the grade is, I think is like, for example, in the Phang Nga, in this case, it's about 2% of lithium oxide is more than cut-off grade already. So it is possible to be mined in the future. So the cut-off grade is, I think, below than, I guess, I'm not quite sure. So 1% up, it should be okay. So, yeah, but I can't answer for the what you call for extraction method. Yeah, thank you.
Okay, how Ikram Mandiri, is the answer is answer the question, one of the question? Oh, okay, thank you. Maybe any audience ask the question?
Bu Aton boleh tanya?
Ya, silakan Rob.
Thank you, Bu Aton. Mr. Abhisit. Based on the geological map that you saw us, we saw that in general, the mineral deposit belt are distributed in trend of more or less north and south directions. They are present in various rocks with different in age. My question is, what the main parameters that control those belts, and what kind of process that responsible for those formation? And the last one, since when the mineral deposit is formed in those belts? Thank you.
Thank you very much for the question. I think it's the main is the control is a tectonic setting. If you look at most of the mineral belt in this region are related to either subduction related, mostly is subduction related. So that is controlled by tectonic setting. If we look for the for exploration, we need to target the subduction related setting. And except one of them, which is hosted in sedimentary hosted, that occur as the Mississippi Valley type. That one in the setting of breathing environments. That is minor. We find in the Western Thailand and further north in Myanmar. That only one exception. The rest are controlled by, the rest occur in the subduction related. So the age all vary. In each belt can have many different age. So we need to study the magmatism, volcanics, and plutonic rock in order to define which one are really responsible for each deposit type. So mainly is tectonic, secondly is magmatism, and the age can be varied from the, let's say that Carboniferous to even younger, Jurassic. And a good example is the Inlay Four Belt, which is from Laos to Thailand. And the mineralization are mainly in the Permo-Triassic, about 200 million years. Although we have different age of igneous, plutonic, and volcanic, but you do have specific age for mineralization. Okay?
Okay, thank you.
Anyone, if any part of the question, if I didn't answer, please let me know.
Okay, thank you.
Okay, terima kasih from Ildram. Maybe any question?
One more question, okay?
Yes.
Yeah, thank you. Sorry,
Yes.
I was wondering, is this in Thailand? Do you have any type of orogenic deposit occur in Thailand side?
Yeah. The clear the orogenic gold or orogenic deposit are not present in Thailand, but as I say, the Sukhothai belt and in Thailand, partly also associated with the metamorphic. But the mineralization itself are hosted in quartz vein. That's why I define preliminary as epithermal, because but hosted in the cataclastic actually, in the metamorphic of Carboniferous, even more than that. So you are right. You make me thinking that maybe I can define as orogenic, because I just put epithermal, but yeah, that also only in the Sukhothai belt, but we don't have any orogenic related in the Lei-Four belt. Yeah.
So we need to study more in detail, yeah?
Yeah, yes.
Because I saw you have many long belt within this metamorphic, yeah. So it should be, could expect some orogenic type deposit within those belt.
Yes, you're right. You're right. Or maybe further north of Laos to Myanmar and all this.
Yeah. It's on Myanmar side, you saw Moditaung is very good example of orogenic deposit. Yeah.
Yes. I visit Morita. I'm currently drafting the manuscript as well. Yes,
okay, thank you.
Thank you very much.
May I have one question again?
Yes, welcome.
Yes,
Mr. Abhisit.
Professor, please.
Yeah, thank you. Mr. Abhisit, concerning the diamond deposit in Indonesia, as we know, we find the diamond alluvial in South Kalimantan. And we know also that diamonds are present in Birmani, maybe in Thailand, also in continental. So that you have idea, is it just diamond are correlated one each other or not?
Thank you. You're right. In Thailand also there is a report about the diamond in the sea, in Andaman Sea. Yeah, but so far they cannot determine with the source of diamond, because surrounding the Andaman Sea near Phuket and Phang or Rayong further north of the Phuket, they don't find any correlation with the geology. So probably some people may expect that maybe the diamond has been transported from Myanmar, from the further. That can be, but I don't know for Kalimantan because that is quite far from this. And diamond, because diamond is actually, it come up from the deep, it forms deeper part of the earth, you know, like 10 kilometer or more. So diamond, as well as the gem bearing the basalt, I mean the what you call gem, beside than diamond. So we know that in Thailand, we have in the eastern Thailand and western Thailand, we Kanchanaburi, we are famous for the sapphire. So the gem, what do you call gemstone. But that also hosted in the basalt. So it means that it brought up from the magma. So the same thing that diamond can probably brought up from underneath in the Kalimantan as well. So it's not related with the what you call the geology in the common of the Indonesia, I think, but maybe the deeper part just bring up to the surface. That's what I guess.
Okay, thank you. Thank you, Pak Abhisit.
Yeah, okay, thank you.
Okay, thank you. Any question from the audience? No, maybe the last question for me, Dr. Abhisit.
Yes, welcome.
Okay, thank you. If we look at your presentation, that I see that variation deposit have a controlled by tectonic setting.
Yes.
For example, the orogenic deposit, where is the hostis rock is a metamorphic. As I know, in the eastern of Indonesia, it is found orogenic deposit gold, but I am still confused how to separate orogenic deposit and epithermal deposit, because if I look at the temperature, it is a similar temperature. For example, the Bombana, the host rock is phyllite and schist, and it is found also. It's also found the epithermal deposit. So how to separate this is the epithermal deposit or the orogenic deposit? Thank you.
Okay, good question. Thank you. So the key difference between these two types of deposit is not only metamorphic. The metamorphic it's a main control because you need a fluid that what you call the gold especially come out from the rock, from the host rock through the metamorphic fluids. So when you talk about epithermal, it's hydrothermal fluid related to magmatism. So that is separate. So what you expect in the physically in the sample, if you identify the orogenic, you don't expect the banding like crustiform, coliform, banding like epithermal deposit. You do have only quartz veins and then with the disseminate sulfide, but you don't expect to see the beautiful banded coliform texture. And the temperature is slightly high, but temperature may be not the key. But you may expect also like isotope, like oxygen isotope. If you do oxygen isotope, you probably find it is metamorphic fluid rather than the meteoric waters. Sorry, metamorphic, yes, you are right, metamorphic fluid rather than the meteoric water. That is a key. But what I have been observed is like in Malaysia also. In one of them also, I did study in the KSO in the Laos. Both of them are orogenic, and they don't have banding. It can be hosted in the low-grade metamorphic to very high-grade metamorphic. That's the key, yeah. But epithermal mainly in Thailand, and not only Thailand, but common epithermal hosted in volcanic. Mainly are hosted. I think Indonesia as well, mainly hosted in the volcanics. So that is a key. Okay, thank you.
Okay, thank you, Doctor. Maybe the last question. Another question? No? Okay, if there is no question, I have to conclude that tectonic setting have control the variation of the deposit type, especially in Southeast Asia. So we can see that your presentation, we have to we can see the variation deposit type like associated magmatic type, hydrothermal type, and orogenic type. Thank you, Dr. Abisid. Your sharing is very interesting. Okay, the next event is presentation of a certificate to the speakers by Prof. Mega as a Dean of Geological Engineering Faculty. Prof. Mega.
Yes, okay, thank you, Bu Aton. To all the presenter, yeah, I think especially Dr. Abi Salam, who is now still present, but I think the other two presenter, Professor Watanabe, I present this certificate as a certificate appreciation for invited speaker today in our webinar series. The second maybe to Dr. Jill. But Dr. Jill also already left maybe from this room because she's have the work to do. And this is a certificate also presented as appreciation for her as an invited speaker in our webinar series. And the last certificate we presently to Dr. Abis Salam. Dr. Masu, thank you very much. This is our certificate appreciation for your talk as an invited speaker in our webinar series. Thank you very much for your contribution to our faculty regarding in our inauguration or 62 our faculty or geological engineering. Thank you very much, Dr. Abisalam.
Thank you very much, and congratulations for your anniversary.
Thank you, thank you.
Okay, thank you once again. Thank you, Dr. Abisat Salam. Okay, ladies and gentlemen, with the completion the third speakers delivering this material, the webinar is over today. Hopefully, the material delivered from speakers can improve our knowledge and give the inspiration or ideas to regarding the management of mineral sources as properly. Okay, goodbye. Happy weekend. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Hatur nuhun, Bu Aton, Bu Santi, Bu Lina, dan semua panitia untuk pelaksanaan webinar pertama. Juga untuk para partisipan yang masih bertahan sampai di akhir sesi ini, mudah-mudahan memberikan manfaat untuk kita semua. Assalamualaikum.
Waalaikumsalam.
Recording stopped.